Hello, 1060 class. Let's start the new material. This first section is called Sample Spaces and Probability. So there are 10 problems. Let's do the first one. It says, write each event as a set of outcomes. And it says, when we roll 2 dice, the total showing is 7. So we want to express this as an event. So usually when you write an event, you use set notation. So notice I'm using the left curly bracket there. And we want the sum of the 2 dice to be 7. So one possibility is that the first one is a 1 and the second one is a 6. Another possibility is the first one is a 2 and the second one is a 5, and so on. 3-4 is a possibility, 4-3 is a possibility, 5-2 is a possibility, and so is 6-1. So every one of these ordered pairs is an outcome in the sample space. And so an event is just a subset of all of the outcomes in the sample space. So this particular event has 6 outcomes in it, but that's your answer. Let's do the second one. And this is really number 5 from the book. Red appears exactly once when we spin the given spinner 2 times. Well, here's the picture that I have in the book. Here's a spinner. And we have 3 possible colors that the arrow could land on. Red, blue, or yellow. So there's the picture. And it says, use the given spinner to write the event as a set of outcomes. And we're supposed to abbreviate red with a little r, blue with a little b, and so on. But it says red appears exactly once when we spin the spinner 2 times. So here's our event. And I'm just going to represent each outcome as a couple of letters. So the first letter is what the spinner lands on the first time we spin it. The second letter is what the spinner lands on the second time we spin it. But for this particular event, we want the red, the R, to appear exactly once. Well, let's assume that it appears first in the first set of outcomes that I'm going to write down. It could be red-blue. It could be red-yellow. And I think that's it for the number of ways for the red to appear exactly once if it's first. But it could also be second. And in that case, you have blue-red or yellow-red. Now, we can't have red-red because in that case, the red would appear twice. And we want the R to appear exactly once. So it looks to me like there are probably just 4 outcomes in this particular sample space. All right. And that's it. That's your answer. So just remember, an event is just a set. It's just a collection of outcomes in the sample space. That's why I'm using set notation, which is what these curly brackets represent. So let's do number 3, which is the next problem in the list. And that's really number 12 in the book, so let's read it. We are flipping 4 coins. Outcomes in the sample space are represented by a string of H's and T's, such as TTHT and HHTT. How many elements are in the sample space is part A. So we're really flipping 4 different coins. Let me try to explain the experiment. So one possibility is maybe they could all be heads. Okay, another possibility is you could have the first coin being a head, the middle 2 coins being a tail, and the last coin being a head. So those are possible outcomes in the sample space. But it says how many elements total are in the sample space. Probably the best way to do this is with a slot diagram. And I'm going to have 4 slots because I have 4 different coins that I'm flipping at the same time. So the first one might be a quarter, nickel, dime, and I don't know, penny. But you're flipping 4 coins. I know that each coin has 2 possible outcomes, heads or tails. So it looks to me like the number of outcomes in the sample space is probably 2 to the 4th or 16. So that's the answer to part A. Total number of outcomes in the sample space. They didn't ask us to list them, just find the number of them. Part B, express the event there are more heads than tails as a set. All right. So more H's than T's, essentially. So let's see if we can systematically list all the possible outcomes that corresponds to that description. Well, more H's than T's, notice that there are exactly 4 letters in every single outcome. So if we have more H's than T's, that means we have to have at least 3 H's, right? So really we just have to list all the outcomes that have at least 3 H's. Well, if we have 4 H's, then it's going to look like this. That's one possible outcome. And if we have exactly 3 H's, that means we have exactly 1 T. So the t could come first, the t could come second, the t could come third, or the t could come fourth. All right, so this is the event right there. And notice, again, I use set notation with those curly brackets. There are 5 outcomes in that particular event. All right, let's do part C from the same problem. Part C says, what is the probability that there are more heads than tails? Okay. So that's what we're looking for. Well, notice that we just found the set that corresponds to all the outcomes that have more heads than tails. So we really just have to use the definition of the probability of an event. So the probability of that particular event is just the number of things in the event divided by the total number of things in the sample space. So that's the definition of the probability of an event that I alluded to before in the notes. And hopefully you read over the PowerPoint slides a little bit before you tried these problems. But basically all you do is count the number of outcomes in E. 1, 2, 3, 4, 5. That's N of E, sometimes referred to as the cardinality of E. And then divided by the total number of outcomes in the sample space. But remember, from part A, we found that there were 16 outcomes in the sample space. So the answer is 5 over 16 for part C. And just to review really quickly, if you kind of skipped over the notes, which you probably shouldn't have done, often we represent a sample space with a Venn diagram, and this is a Venn diagram. And you might have several possible outcomes in your sample space. So it just depends on what the experiment is. In my little example, I'm going to assume that there are 4 possible outcomes. So you might be rolling a 4-sided die, and one of the numbers that comes up might be a 1, 2, 3, or 4. Okay? So here are all the possible outcomes. But anytime you take a collection of outcomes, that is referred to as an event. So every individual outcome is just an outcome, but a collection of outcomes is an event, and the whole thing is the sample space. All right? So when I talk about the definition of the probability of an event, it's just the number of those outcomes in the event divided by the total number of outcomes in the sample space. So for the example that I just wrote down, the probability of this event, and by the way, usually we use capital letters to represent events. It's just the number of things in the event divided by the total number of things in the sample space. So in this case, there are 2 outcomes in that event, but there are 4 total in the sample space. So the probability that A occurs is 1 over 2. So that's just a kind of a quick review of some probability theory. But that was part C. Let's do part D of that same problem. It's a good problem. What is the probability that there are an equal number of heads and tails? All right. So I guess it would be a good idea to list the event corresponding to that first, list all the possible outcomes that would satisfy that. So once again, we're going to have a string of 4 H's and T's because we're flipping 4 coins, all right? But if we have an equal number of them, that means we have to have exactly 2 H's and exactly 2 T's. So let's list all the ways for that to happen. Well, the H's could come at the beginning, the H's could come at the end, or they could alternate. But you also might have the T's in the middle, or you could have the T's at the end. And I think that's it. So there are 6 ways for there to be an equal number of H's and T's. All right? But D says, what is the probability that there are an equal number of H's and T's? So you don't want to just list the outcomes in the event. You want to find the probability of that event. All right? But just use the definition. It's the number of things in E divided by the total number of things in the sample space. Well, you can see that there are 6 things in E, and from part A, we know that there were 16 outcomes in the sample space. And make sure that you reduce the fraction. If you divide by 2, that turns into 3/8. So you should reduce the fraction when you do these. So that was kind of a whopper of a problem, but that was number 3. Let's do number 4, which is kind of like number 27 in the book. And I'll read it to you. In a given year, 2,048,861 males and 1,951,379 females were born in the United States. If a child is selected randomly from this group, what is the probability that it is a female? Okay. So let me write down the total number of males, 2048,861. And the total number of females, 1951,379. So that was in a given year. And it says, if a child is selected randomly from this group, what is the probability that it is female? So we're looking for the probability that it's female. Well, all that is the number of females divided by the total. All right. So just plug all that into a calculator. And you might want to put your bottom in parentheses there because it is a sum. But if we round it to the nearest hundredth, I get about 0.49. So that one was a lot easier than the one before it, but not quite as interesting. Let's do number 5. The cookie problem. Okay, so this one says that we have a collection of Girl Scout cookies. We have 16 mints, 28 caramels, $12 shortbreads, and 24 shout-outs. So those are all the cookies. And it says, find the probability that we get exactly, or that we pick a thin mint when we select exactly one cookie at random. So we're looking for the probability that we get a mint. All right. So that's kind of easy. All you do is count the number of mints in the basket, which is 16, and then divide it by the total number of cookies. So plug all that into a calculator. And I get 0.2. So notice that our probability is between 0 and 1, and I'll just kind of mention this in passing. The probability of any event is always between 0 and 1, inclusive. So if the probability is 0, the event is impossible, it never happens. If the probability of the event is 1, it is certain to happen. But most of the time, the probability of something is between 0 and 1. Strictly between 0 and 1, even though the ends are possible. I think I'll skip 31 because it's kind of similar to 29, and that's really number 6 that I'm skipping from your homework. So let's move on to number 51 in the book, which is really number 7 in your list. And they refer to a table on this one. So let me do my best to reproduce the table for you. And I looked, the one in your homework is kind of similar to this. Well, let me see if I can construct the table for you. I'll just do it on a fresh sheet of paper. So we have two categories horizontally, males and females. And it looks like we have four categories vertically. The first one is married. And then we have widowed. And then we have divorced or separated. I'll just say divorced. And then we have never married. All right. And then we fill in the table with numbers. So this first one is 9740, and we'll go ahead and fill it in. Okay, so let's read the problem. What do they want us to do with this table? Well, we'll find out. It says, if we pick a divorced or separated person, what is that probability that the person is a woman? So let me show you how to do these. It says we're only focusing on divorced or separated people. So we only focus on this particular column. That's the given. It's almost kind of like a conditional probability problem, but not quite. But if we pick a divorced or separated person, what is the probability that the person is a woman? So if you only focus on this column, and I say, what's the probability the person is a woman? All you do is take the number of women in that column and divide it by the total number of people only in that column. All right? And plug that into your calculator. So let's see what we get. Okay, so I get 0.59. So once again, notice the probability is a number between 0 and 1. Well, let's do the next one on the list. And in fact, I think the next one is too similar to this one. I'm going to skip it. Let's do number 9 from your homework, which is really number 19 in the book. This one really is kind of different. Assuming we are drawing 5 cards from a standard 52 card deck, what is the probability that all cards are diamonds? So this one is a little tricky. We're going to draw 5 cards from the deck, and we want to find the probability that they're all diamonds. All right. And there are 52 cards in the deck. You should know that there are 52 cards in a standard deck of cards. And let me just say a couple of things about that too. If I didn't mention this in class already, the suits are diamonds, hearts, clubs, and spades. Okay? And the ranks, well, those are the numbers on the cards. So the first rank might be an ace, I guess, depending on how you look at it. If you think of the ace as a 1. Well, then we also have a 2, a 3, a 4, all the way up to a 10, and then a jack, queen, king. Okay, so you actually have 4 suits, and you have 13 ranks. So just something to keep in mind for some future problems in the course. Well, let's see if we can figure out this one. It says we're going to draw 5 cards. What's the probability that they're all diamonds? This one is kind of tricky, so I got to show you how to do it. Okay. So the event is that we get all 5 cards big diamonds. So we have to count the number of ways for that to happen. Well, how many diamonds are there total in the deck? There are actually 13. So 13 choose 5 combinations is the total number of ways that we can select 5 diamonds. All right. So there are always 13 of each one of these suits. There are 13 diamonds, 13 hearts, 13 clubs, and 13 spades. So this is the total number of ways for all the cards to be diamonds. It's just the number of ways to choose 5 out of those 13 diamonds, okay? But remember, we actually have 52 cards total, and 52 choose 5 is the total number of ways that we can draw 5 cards in general. So you really just have to take the ratio of those two combinations to get the answer. And that is kind of tricky. So let's use a calculator. And maybe I'll kind of review with both calculators, starting with this one. So 13 choose 5. Remember, you enter the 13 first, and then go to math, probability, use the combination symbol. So 1287 is the number on the top. But now let's do 52 choose 5, which is going to be a lot bigger. So it's that huge number. Well, let's take the ratio of those two guys. Okay, so notice that my calculator gave me the answer in scientific notation. This little e -4 means times 10 to the -4. So let me show you how you can deal with that a little bit. So my answer says this is 4.95 times 10 to the -4, essentially. So all that means is if you want to put this in standard notation, you have to move the decimal to the left 4 places. So that means you want to insert some zeros in front of that 4. Because the decimal starts out being right there. If you move it to the left 4 places, 1, 2, 3, 4, it looks like you're going to have 3 zeros in front of that 4. So in ordinary notation, 0.000495 is your answer. So kind of tricky. And I think the last one is also a little bit tricky, number 10. This is number 21 in the book. Let's read it. What is the probability that all cards are of the same suit? So remember, a suit is just one of the diamonds, clubs, hearts, or spades. So when you say, what is the probability that they're all of the same suit, you're really saying, what's the probability that they're either all diamonds, or all hearts, or all clubs, or all spades? Well, we just calculated the probability that they're all diamonds, which is this. So all you would do is just basically multiply that by 4. Because for every suit, this is the probability that you get cards only of that one suit. So you would really just be adding up 4 of these guys. But you could do it a lot faster just by multiplying it by 4. So that's the quick way to do it. And here's what I get in ordinary notation. All right. Now, I don't know how they want you to round this. They're probably going to tell you in the computer how to round it. But we could also round it to 3 places. And if we did, it would be 0.002. So hopefully that clears up some of the confusion about this probability stuff. I tried to review some of the concepts for you a little bit. But make sure you read over those PowerPoint slides too, because this stuff is not easy if you're trying to learn it on your own. But that's it for this video.